All right, and then because of my traveling schedule, I will need to cancel our Thursday office hour this week. And for that, I'll host additional Q&A session today after class. I'll probably also host additional office hour next week. So I have asked Dr. Anderson to record her lecture. If she didn't do so, I'll also make my own copy for the Friday lecture. Also, I have posted TA office hours on Canvas. You should be able to find it on the module of our week 1. So those are also very good resources for you to use. All right, and since we're on Zoom, if you have any questions, feel free to raise your hand or post it on the chat. To answer someone's question, the Friday lecture will be in person. Dr. Anderson will be here in class with you for the Friday lecture. Our Wednesday lecture will probably also be in person. I haven't decided yet. It depends on how I recover, but it should be in person. So you should assume all lectures are in person unless there is a separate message or announcement said otherwise. All right, any additional questions on the announcement? All right, so let's move on to where we left over, which is Lewis acid base. So in our last week's lecture, we went over the Bronsted acid base, which is the conventional definition of acid-base chemistry. So remember, in the Bronsted acid-base chemistry, we were saying an acid is a proton donor. It donates a H+ or a proton, where a base is a proton acceptor. It accepts a proton to form a neutral species. In organic chemistry, more often we're dealing with another concept called Lewis acid base. So the idea here is similar to the Bronsted acid, but slightly different in some other way. In Lewis acid base, we are not necessarily working with charged species. Rather, we have new definition of Lewis acid and Lewis base. So for example, this example we show several times, right? So we can do the arrow pushing here, starting from the nucleophilic lone pair of the ether, attacking the boron species, which is partially positive because of all the electron withdrawing fluorine groups around. So here, the definition of Lewis acids are electron pair acceptors. Or we can call them electrophiles. Alternatively, we also have Lewis base, which is a new definition here. So Lewis bases have available electron pairs, or the definition of the Lewis base are electron pair donors. We also call them nucleophiles. All right, so the electron pair donor and acceptor are the new definition for the Lewis acid-base chemistry. In organic chemistry, you'll see some typical Lewis acid. So when we say it is Lewis acid, normally we're talking about a species that has an electrophilic center. So like the BF3 we say here, you can have aluminum F3. So here X just stands for halogen. So you can have aluminum halogen, magnesium halogen, boron halogen. So any species that has a electron deficient center or unfilled valence shell. For typical Lewis bases, there's a typo. we're talking about electron pair donor. So naturally, electron pair donor will have a lone pair to donate its electron into some other species. So I'm showing here some typical Lewis bases. Well, one common thing is they all have lone pairs. As an additional information, the alkenes can also act as Lewis bases. So the pi bond in your alkene can also act as Lewis bases. All right. And Lewis acid-base reaction in organic chemistry is just very common. We've seen several examples before, and let's just do one again. So here we're talking about an example of the electrophilic substitution. So in this class, what I expect you to know is, for example, if I give you the reactant and the product, can you identify the nucleophile and electrophile in this reaction and do an arrow pushing to complete the reaction mechanism? So here, what we can see is the OH minus, apparently oxygen, has lone pair, so it acts as a nucleophile or a Lewis base. And on the right-hand side in the alkane halogen, because of the chlorine being more electronegative compared to carbon, this carbon here is more electrophilic. Right, and we can use the arrow pushing to complete the reaction mechanism. Start from the electrophile, attacking the nucleophile, and then we break the carbon-chlorine bonds to get the product. So this is just one example. In this example, we have a anionic nucleophile and we have a neutral electrophile. Alternatively, you could also have a neutral electrophile like NH3. So this is our nucleophile or the electron pair donor or Lewis acid or Lewis base, sorry. And in this reaction, what we have is the lone pair of NH3 attacking the carbon here and the iodine left. And we end up with a substitution reaction to form a cationic species here and a neutral species here. So the overall charge needs to be balanced up. All right, and as a quick summary, for our Lewis acid-base reaction, again, this is another example. We can have a nucleophilic iodine minus or a Lewis base. So your nucleophile or the Lewis base always have a lone pair. And your electrophile here is your carbon center here. We can push the arrow towards the carbon, break that bond. So in general, when we are saying nucleophile, all nucleophiles are Lewis bases or they're electron pair donors. And all Lewis acids are electrophiles, which means they're electron pair acceptors. There are minor differences between nucleophile and Lewis base and between Lewis acid and electrophile, but for this class, we can treat them as similar terminologies. And later in this lecture, we'll be talking about functional group, which in this case, the CBr bond is a structural feature that directs the chemical reactivity. We have all the CH bond around, but they are relatively inert toward chemical reactions. And this CBr, or the carbon halogen bonds, is where the chemistry takes place. And that we call it a functional group. So before we went into discussion on functional groups, let's see if we have any questions on Lewis acid base. You can post it in the chat or raise your hand. I'll leave 2 minutes for you to do that. All right, so here what we were talking about is all right, so I got 3 questions, and let's just go by it one by one. So the first question is, do we still have conjugate acid and base in Lewis acid base reactions? The quick answer is no. The conjugate acid and base concept only applies to Bronsted acid base reactions. When we're talking about Lewis acid base, we don't have that similar type of concepts. And secondly, the question is Lewis acid the same as Bronsted base? So the answer is no. There are 2 very different concepts. A Lewis acid is saying it is electrophilic. It accepts electron pair. Alternatively, in the Bronsted acid-base chemistry, a Bronsted base accepts proton. So the quick answer is the Bronsted acid base and the Lewis acid base are 2 different sets of acid-base chemistry. They are related, but they're not the same. The other question we have is, what's the relationship between electrophile, nucleophile, and Lewis acid and Lewis base? So when we say, let's back to this example. We have a Lewis base or a nucleophile. Again, what that means is this species, this highlighted iodine minus species, is my electron pair donor. All right, so these terms are similar terms to each other. Likewise, the green term here, this carbon center here is has a partial positive charge because of the electronegativity difference. So it is an electron pair acceptor. Or it's Lewis acidic, or it's electrophilic. So when we're doing the arrow pushing mechanism, when we're saying the lone pair is attacking the electrophilic carbon center, what you can imagine is this lone pair is transferred onto this carbon center because of the attraction between that negative charge and the partial positive charge. So the Lewis acid-base reaction is similar to the Coulomb's interaction. You're just imagining the acid-base reaction between a negative charge species and a partially positive charge species. And if you think about it, what's the definition of the Lewis acid and base? You should be able to derive whether a species is acting as a nucleophile or acting as a Lewis base by just looking at the structure. Does it have additional lone pair it wants to donate? So that's about all the time I have for questions for now. I'll stay up after 11:50 for more questions if you want to stay. All right, so let's now move on to look at functional groups. So for rest of today's lecture, we'll be talking about a lot of different functional groups. Again, functional groups, they are the center of reactivity, or functional groups are the structural feature that tells us whether or not a molecule is active, is chemically reactive. So we will start from the most common functional group, which are hydrocarbons. Hydrocarbons, by its name, it only contains hydrogen and carbon atoms. The first and the most simple class of the hydrocarbon functional group are alkanes, or occasionally we also call them alkyl groups. So these functional groups are single bonds only. They're nonpolar. They're relatively unreactive. For example, these are some of the nomenclature we can follow when we're talking about functional groups for the alkenes or alkyl groups, right? So CH4, the actual name, IUPAC name for CH4 is methane. And when it acts as a functional group, we call it a methyl group. Likewise, we can have propane, which is the IUPAC name of C3H8. We can have two different types of propyl group. You have the linear propyl group or the isopropyl group, depending on which is the position of your bonding. Alternatively, when you have a cyclic structure, you can also have a cyclohexane. So here, cyclo means it is the ring. Hexane means if you count it, 1, 2, 3, 4, 5, 6, we have a total of 6 carbon. So hex stands for that 6. So the functional group of that cyclohexane is called a cyclohexyl group. So here I'm just using this wiggle line to tell you there's something bonded to this position, whether it's another carbon atom, whether it's another group, it's just something that's bonded to that carbon. Something's bonded to this carbon. We don't know what that is. So nomenclatures are part of organic chemistry. I'll probably not test you too much on nomenclature, but the idea here is I tell you to identify the isopropyl group in a complex molecule. You should be able to address where that is. So that's the alkene group. It's not very chemically reactive. So what I expect you to know is, first of all, when we're saying alkyl group, like methyl group, ethyl group, you should know what I'm talking about. Also in organic chemistry, we abbreviate alkyl groups in R, just saying they're just hydrocarbons, single bonds, not very reactive. All right, so that's the alkane and alkyl group. Next up, alkene or double bonded species. So alkene will have alkynyl group. You will be talking about reactions of an alkynyl group in chapters 11 and 12. I will not go over them in detail. You'll learn that in 14B. But before we do that, what I do want you to know is alkenes are somewhat special. As we were talking about, alkenes has the pi bonds. So these pi electrons here, they can act as nucleophiles. Remember what nucleophile means as electron pair donor. Or Lewis basic. All right, so alkenes are chemically more relevant comparing to the alkyl group we talked about because of the double bonds. One of the typical example reaction we showed before is, for example, the electrophilic addition to the double bond. The electrophilic tells you it's your double bond is reacting with the electrophilic species. So here is H+, but it can be any other electrophile you think about. We use a different color to keep it consistent. So in this reaction, the way to do our arrow pushing is we start from the alkene, because our alkene now is acting as a nucleophile. So the electrons in the alkene, the electrons in the pi bonds is attacking the electrophilic H+ to form the new CH bond. And what we end up here is a carbocation intermediate. All right. Likewise, the triple bonds in the alkyne species can also act as Lewis bases. So it's the same idea. We have the pi bonds, we have the pi electrons, and these pi electrons can act as nucleophiles. So that's the first piece of information. Second piece of information is, if you remember what we talked about. So here, when we say R or H, it's depending on whether it's a R group or an H group. But if it is an H group, so this is again a review. So remember the SPCH is more acidic. Than SP3. pH. So this is a review of our Bronsted acid-base chemistry. And as a result of these properties, in chapter 13, you'll see some special chemical reactions of the alkyne group. So again, what I expect you to know is we covered so many like acid-base reactions, acid-base chemistry, Lewis acid and Lewis base. What I hope you know is looking at these functional group and get an idea which part of the molecule is nucleophile, which part of the molecule is acidic. What are we talking about? What are the potential reactivity of these reactions? So for example, in this alkyne group, when we're saying this is a H, we're saying, hey, we have a hydrogen bonded to this triple bond carbon, or we can have an R group bonded here. Hydrogen is abbreviating for hydrogen, no mysterious. The last class of hydrocarbon is called arenes or aryl group. We'll talk more about aryl group and especially focusing on their structures and special properties in lecture 15. Aryl group, exemplified by benzene, they have very special properties because of the large stabilization factor coming from the resonance stabilization. All right. So this is the hydrocarbon we were talking about. I got some question about what this notation means. So this just means this group can either be a R group or a hydrogen. So in both cases, when we're writing it like R, parenthesis hydrogen, it's the same notation in your textbook. What we're saying is this group can either be an alkyl group or a R group. And we just talk about alkyl group. Examples of alkyl groups can be methyl group, ethyl group, isopropyl group. So anything only have carbon-hydrogen single bonds. It can also be just a simple hydrogen. All right. Let's see if we have any questions before I move on for hydrocarbons. So one question comes here is, what if a molecule has some single bond and some double bond? And the quick answer is, yes, we will see some complicated molecules with multiple functional group. So whenever we're talking about, for example, here is a good example. We have a double bond, carbon-carbon double bond in here. But at the end, we have carbon-hydrogen single bonds. So in any organic molecule, you can have multiple functional groups that come to play. The important thing is by understanding the properties of each functional group, you can get an idea about how the molecule can behave. And for the array stability, the resonance structure is one factor, and we will be talking about more about arrays in lecture 15, so stay tuned. All right, so I'll take more questions after 11:50, and let's just move on to look at some other functional groups. The next class of functional group are functional group with polar covalent bonds. So again, functional groups, they are the center of chemical reactivity. We look at a molecule, we search for its functional group, and we try to get some idea about how this molecule is going to behave. For one example, a functional group with polar covalent bond is apparently you can have halogen bonded to a carbon center. So examples of haloalkenes will be alkyl group or R group. And again, example of our alkyl group can be methyl group or ethyl group. Or isopropyl group, etc., etc. And in here, this X means some kind of halogen, or X equals to fluorine, chlorine, bromine, iodine, etc. Typically, because of the electronegativity differences, when you have haloalkenes, what we end up with is your carbon center here to act as a relatively electron deficient species. We've seen this example several times. For example, if I have a methyl group bonded to some kind of halogen, so I use the general form here just for generosity, you have some kind of nucleophile, and this carbon center would have a partial positive charge, and the halogen would have a partial negative charge. So this is a generalized nucleophilic substitution reaction where the electron on the nucleophile attacks the relatively electron deficient carbon center, and we break the CX bonds. And what we end up with is CH3 attached to a nucleophile, and we end up with a halogen. So depending on what your molecule you have, you might end up with a plus charge and a minus on the new species and the anionic species on your halogen. Or in the other words, it's because this alkyl group, carbon is more electron positive comparing to halogen, we're expecting it to act as a more electrophilic species. or the other way to put it is we can say the carbon attached to a halogen is Lewis acidic. All right, this is the first class, the haloalkanes. Next up, alcohols. So when we say alcohols, what we're having is a OH group bonded to some species. So an example here, we're using ethanol. All right, so ethanol is we have a ethyl group bonded to an alcohol. So let's just look at this ethanol and think about what are the possible activity center of ethanol. Remember, we were talking about the idea of electrophile being electron pair donor, electron pair acceptor, and nucleophile being electron pair donor. So in this case, on the alcohol, my oxygen have lone pairs that can potentially act as nucleophile. Alternatively, the center carbon here, because it's bonded to a electronegative atom, oxygen, it can act as electrophile. On top of the Lewis acid base, if we just look at this hydrogen here, it's bonded to a very electronegative species, which is oxygen. Upon deprotonation, we can form its conjugate base, which is an oxygen-centered anion. So this hydrogen here is a relatively acidic hydrogen. And again, here when we're saying it's relatively acidic, we're referring to the Bronsted acid-base chemistry. All right, so everything here boils down to two sets of simple concepts. Lewis acid base, Lewis acid, electron pair acceptor, electrophilic. Lewis base, electron pair donor, nucleophilic. And then when we switch gear, we have Bronsted acid base. Bronsted acid donates electron, forms stable conjugate base. Bronsted base accepts electron. So there are two different sets of acid-base chemistry ongoing. Both of them works when we're talking about reactivity of a specific molecule in organic chemistry. And what I expect you to know is, let's say, given any molecule, you can analyze what are the potential roles this molecule can play in some kind of chemical reaction by just looking at their functional group and understand how these functional group can act in a organic chemistry reaction. We'll see some example together. So this part is the alcohol. And again, for functional groups, we will be using nomenclatures from now on. For example, we start talking about alcohols will react, blah, blah, blah. We use NMR to identify like alcohol groups or alkenes. So I won't test you very heavily on nomenclature, but we will start to use vocabularies like alcohols, alkenes, ethers, aldehyde, etc., etc. So you do want to get familiar with these vocabulary. All right, moving on. Next functional group, ethers. So ethers have the general formula of R group attached to an oxygen, and then the oxygen attached to another R group. So again, R group here are my alkyl groups. Note that we have R and then R prime. So R prime just tells you it is a different alkyl group. And apparently in ether, like alcohol, we have two modes of reactivity. Your center oxygen has lone pairs that can potentially act as a nucleophile. And then alternatively, your carbons attached to the oxygen will have the partial positive charge, and they can act as weak electrophiles. In the same family of the ether, we have thiols. So thiols are similar to ether. We can see their general formula is very similar, just instead of oxygen in the center, we have a sulfur atom in the center. So as a result, our sulfur is not as electronegative as oxygen. So sulfur is the only nucleophile, a steel nucleophile in this in the thiol group, but the R group is less likely to act as electrophiles. And just remember, when we are writing R group and R prime, what we are saying is this R group are some general alkyl groups. All right, so in any general alkyl group, you have like CH2, CH3, or CH3, etc., etc. So it's always a carbon atom bonded here and here. All right, and the last polar covalent bond we'll talk about is amine. So here we have a center nitrogen. The center nitrogen is forming 3 single bonds with 3 alkyl groups. And in here, our center nitrogen has a lone pair, so it can act as a good nucleophile. So before we move on, I want to use this as an opportunity to quickly clear out some ambiguity in the R group. So in this molecule, let's imagine R equals to methyl, R prime equals to ethyl, and then this R double prime equals to isopropyl. So what is the actual bond line formula of this amine? So we have nitrogen, and here we have a R equals to methyl, R prime equals to ethyl, and then R double prime equals to isopropyl. All right, so this R equals to methyl, R prime equals to ethyl, and R double prime equals to isopropyl. So R is just a general form for any alkyl group. All right. We have 10 more minutes, and let's work on our last topic, which is the functional group with carbon heteroatom pi bonds or double bonds. So this class of molecule is pretty special. It's because of this double bonds to the heteroatoms. What we end up with is the same molecule can have two different reactivity centers that are relatively speaking close to each other. So they can actually react with themselves to form dimers. You'll see those reactions later on. So the typical class of example we have is carbon bonded to a oxygen via a double bond. So in here, we have aldehydes and ketones. They're pretty similar. The general formula for aldehydes, you have a R group bonded to the carbonyl carbon. At the end, you have a hydrogen. Where in the keton, on the both ends, you have alkyl groups. So if we look at the structure of aldehyde and ketones, what we have is in this oxygen carbon double bonds, we have two different types of reactivity you can imagine. For example, the top oxygen can act as a nucleophile because it has the free lone pair. It can donate its lone pair to form new chemical bonds. It's Lewis basic or electron pair donor. Alternatively, when we're talking about a carbonyl carbon, what we're talking about is this carbon right here. So again, this carbon here is bonded to an electronegative oxygen atom. So this carbon is an electrophilic carbon. It's Lewis acidic. And its electron pair acceptor. Right, so the same idea can also apply to ketones as in aldehydes. In ketones, again, on the top, we have the nucleophilic oxygen. And we have the electrophilic carbonyl carbon. Right. And we'll spend a little bit more time looking at the carbonyl group, and then we'll pause. So when we're talking about carbonyl group, because of the special property of this carbonyl group, you have an electrophilic carbonyl carbon. You also have a nucleophilic oxygen. So the same chemical reaction can undergo via very different reaction mechanisms depending on what kind of reaction conditions are available. So first example, you can have acidic condition where your ketone is reacting with a acid. And then in the reaction mixture, because it's acidic condition, you can only have a neutral nucleophile like H and U. So what does this reaction looks like? Again, if I give you all the reactive species, can you do the arrow pushing mechanism to complete this process? How should we do it? The first reaction is here. We have the nucleophilic carbonyl oxygen attacking the H+. And the result is we're forming the species. It's a oxygen-centered cation. And in this process, now with a neutral nucleophile like an ammonia, what we can have is it's attacking the carbonyl carbon, and we're moving that chemical bond onto the oxygen. What we end up with is a species like this. We also call it a tetrahedral intermediate. And the last step here is we're breaking NH bonds, and we're regenerating our H plus. So this one is called the acid catalyzed nucleophilic addition or hydration. So this stands for an intermediate. So an intermediate means this is formed in a short time period, and then it will get used up in the next reaction. All right. The same type of reaction can also undergo via a base catalyzed reaction. Oh yeah, thank you for that reminder. There should be this one we should have pushed it this way because we're leaving, we have a H plus leaving. We don't have an electron on the hydrogen. Thank you for the reminder. We can also have the reaction undergo a basic condition. So in a basic condition, now we have, say, OH minus acting as a nucleophile. And the OH minus attacks the electrophilic carbonyl carbon, and the electron goes on here to the oxygen. Similarly, we're forming our tetrahedral intermediate. And in the tetrahedral intermediate, we have the oxygen-centered anion attacking the hydrogen and goes on to the oxygen. And what we end up with the species and the OH minus. All right, so it's the nucleophile adding onto the carbonyl carbon. In both reactions, we have nucleophile added onto the carbonyl carbon as a product, but the reaction mechanism is very different depending on what kind of condition you have. Your carbonyl species can undergo two different types of reaction. All right, so we are running out of time for today. We'll pick up on Wednesday to finish talking about other functional group. You can also take a look at our annotated notes in what's being covered today. All right, let's see if we have any questions. So one question we have is in here, where is the electron go? So if you think about it, before this oxygen only have one lone pair and it has a positive charge on it. And after the error pushing, the electron in the double bond moved on to the oxygen. And if we draw out all the oxygen, you can see the oxygen now have two lone pairs, and that's where the electrons are. So for functional groups, to be honest, the best way to practice functional group, you'll also see that in my example. So just pick a complicated organic molecule and just do it yourself. It's like, do I know what are these functional groups here? For example, this one is an alkyl group, only have carbon and hydrogen. This one, we have the CO double bond and OH, so it's an amide. That's the halo alkanes we're having. So the best way to practice for functional group, you'll also see that in discussion worksheet. Just get a complicated organic molecule and start talking about it and see, do you have vocabulary for organic chemistry? And going back to this part, I have two more questions. Let's see. The first question, yes, so in this case, this one is called the acid catalyzed nucleophilic addition to the ketone, and the bottom is called a base catalyzed reaction. We haven't covered catalysis yet, so I've been hiding that. And the reason we're calling it catalyzed reaction is here we start from an H+, we ended up with an H+. So H+ is not being used up in this reaction, but it is involved in facilitating the reaction mechanism. The quick answer is I do not expect you to know how to write out this entire mechanism. What I expect you to know is, for example, if I give you all this condition and I can ask you, like, what is the reactivity? Where is the reactivity coming from? What is the nucleophilic part and the electrophilic part of your starting material? And how to do the arrow pushing to finish this entire mechanism. And for the alkyl group, no, it's not just methane, propane, and cyclohexane. So any group that only have carbon, hydrogen single bond are called alkyl group. It can be super long. In fatty acids, you can have like CH2 and maybe 18, and then end up with CH3. That is also an alkyl group. So it can be a super long group or something like this. It can be really complicated, but anything that only have single CH bond will be called an alkyl group. I don't think search for different functional group is a good way to study for this part. In organic chemistry, we have much more functional group than we will be covering in this class. My recommendation is, again, you find a relatively complicated organic molecule and start practicing. Can you identify all the functional group we discussed in this complicated organic molecule? That's the best way to practice for it. So if you go to ACS, they have a molecule of the week. So you should be able to see that, or like search any organic chemistry paper or drug library. Well, so let me see. 1 second, I'll post it. So this is the link I'm referring to. It's called ACS, Molecule of the Week. You should be able to see what are the molecule they post every week to tell you information about that molecule as well. All right, I'll pause here. I'll go grab some water, but welcome to come back for more Q&A around 11:50. All right. See you on Wednesday.